Welcome to my presentation. I am Mohammad Jalaei from Tampere University, Finland. The topic is about employing a continuum damage model to predict fatigue life.
Somehow closed.
Yeah. Fatigue life through Abaqus. The content includes introduction, implementation and analysis, results, and conclusion. A fundamental approach for high cycle fatigue based on evolution equations proposed by Ottosen and his colleagues in 2008. The Ottosen model offers some advantages in comparison with other traditional methods like rainflow and some other fields. In the Ottosen model, unified treatment of stress history is used. It uses a continuum mechanic approach which treats uniaxial and multiaxial stress states in a unified manner, making it more suitable for complex arbitrary load histories. And it uses evolution equations, incremental relations, instead of changes per cycle. In this research, we use a unified low cycle, high cycle fatigue model, which combines high cycle model based on Ottosen equation and low cycle fatigue damage evolution law. The main components of the model include endurance surface. The high cycle part of the model is based on the concept of moving endurance surface in the stress space. Plasticity model for macroscopic plastic behavior in the low cycle fatigue region, and evolution equations. Low cycle fatigue and high cycle models are connected via the damage evolution equation. The original form of Ottosen is based on beta. Beta shows endurance surface in the stress state. As you can see, beta depends on stress tensor, sigma, and some internal parameters that would be calibrated by experimental tests. And as I said before, this method is based on evolution equations. Alpha dot, it depends on sigma and beta dot, and D dot is damage evolution, depends on beta dot and D and B. Evolution equations based on Ottosen article is like this equation. As you can see, there are some high cycle parameters like C, K, and L. These are high cycle fatigue parameters that can which obtained by experimental tests. In this method, as I said before, there is an endurance surface. As you can see, beta is endurance surface, and alpha means back stress tensor, which memorizes the load history, is responsible for movement of the endurance surface. If the stress state inside the surface, beta is less than 0, so no damage developments occurs. While if the stress state outside the surface, beta is bigger than 0 and damage may develop. It is an essential rule to develop the damage, but it is not enough. As you can see, this surface is related to loading case and unloading case. Movement of the endurance surface or beta and damage growth occur when the stress is outside beta or beta is bigger than 0, beta is positive, and moving away from it. It means that d beta is bigger than 0. So if we have this condition, beta and d beta, both of them are positive, so damage can develop. But if just beta is positive, otherwise d beta is negative, so the damage development cannot occur. When the stress is outside beta, but moving towards it, damage and back stress don't evolve. So these conditions are very essential to development of the damage. Beta and d beta, both of them must be positive. This is the original beta or endurance surface based on Ottosen equation. As you can see, sigma OE and A are two parameters can be obtained by experimental test. Sigma OE is endurance limit at 0 mean stress, and A is a slope in the high diagram, as you can see in this diagram. And we can derive A based on this equation, sigma -1 over sigma 0 -1. In this equation, sigma -1 is sigma amplitude fatigue at fully reversed loading, and sigma 0 is sigma amplitude fatigue at pulsating loading. I1 is the first invariant that is traced as sigma. In this equation, we have another parameter, sigma bar effective is its reduced effective stress, and we can derive these parameters based this equation. In this equation, S is deviatoric stress, can be extracted by this equation, and I is the identified tensor. As I mentioned before, alpha is backstress tensor, defining the center point of the endurance surface in the deviatoric plane, and is responsible to memorize the loading history. As I said before, the original Ottosen equation was related to just high cycle fatigue. We wanted to extend this equation. This term is related to low cycle fatigue. I mean, the left term is related to Ottosen, and the right term is related to low cycle fatigue. In this term, we have M and Q. These are low cycle fatigue parameters that can be calibrated by experimental test, and sigma effective P is effective plastic strain that can be obtained by this equation. To obtain M and Q, which are low cycle fatigue parameters, we need at least 2 standard cyclic tests in the low cycle fatigue, and we can obtain these parameters based on this equation. As you can see in this equation, we need epsilon A, P, and N that can be obtained based on experimental tests. As you know, in low cycle fatigue, usually delta epsilon P is bigger than delta epsilon E. It means that plasticity is more important in low cycle fatigue rather than high cycle fatigue, but in high cycle fatigue, plasticity is more important. To obtain these parameters, we need some extra equation. I mean, Coffin-Munson equation, as you can see, and you know, as epsilon A based on this equation is a summation of elastic plus plastic, and can obtain by this equation that the left side, the left term is related to elastic, and second one is related to the plasticity. Another equation is related is Romberg-Osgood equation, because we want to drive the sigma epsilon curve. So we need this equation to obtain some data. Combining the Coffin-Munson and plastic part of Romberg-Osgood, we can obtain the finalized Q and M. As you can see, this is the finalized Q and M and beta. There are some parameters that can be obtained by experimental test. After that, we can extract Q and M, or we can calibrate them. One of our colleagues is from Padova University in Italy. They done some experimental tests to obtain some results. As you can see, they provided cyclic stress strain curve to obtain Romberg-Osgood parameters, NSC and sigma prim C, and also they provided Manson-Coffin curve to obtain some other parameters. The material that's used in our project is 42 chrome molybdenum 4 quench and tempered, and we use strain control. I mean the R epsilon is -1. to obtain some results in low cycle, because plasticity is more important. So we have to apply hardening model. So we need some hardening parameters. The relation between amplitude of uniaxial stress, sigma A amplitude, and plastic strain is as this equation based on this article. Applying the best fit to the cyclic stress strain relation presented by Romberg-Osgood expression, the value of material parameters, I mean gamma and C, can be obtained. As I said in the previous slides, cyclic symmetric strain control tests at different strain amplitudes have been done by Padova University. Based on their diagram, we can obtain sigma prim C and NSC, and then based on optimization, we can obtain CI and gamma that are nonlinear kinematic hardening parameters. As you can see, there is a good verification between the Romberg-Osgood diagram and Chaboche hardening parameters. In our model, we used Abaqus U-worm subroutine to simulate the model and obtain the damage development. U-worm subroutine, user subroutine to generate elements output. And in Abaqus, when we want to obtain some special boundary conditions or some special equation that we cannot apply them in CAE, so we have to write some subroutine based on our requirements. The U-worm subroutine Abaqus is used when we need to define and store user-defined state variables at material integration points during an analysis. This state variable can be used to track additional information that is not directly available in Abaqus CAE. This is a sample of interface in U-worm. Based on the experimental specimens, we modeled this specimen in Abaqus, and we obtained U-worm 13 means damage. Damage for different number of cycles. As you can see, with increasing the number of cycles, the value of damage increases. And this slide is related to some results obtained by U-worm subroutine. You can see based on this is related to low high cycle fatigue and the high cycle fatigue. And this is the variation of damage value based on number of cycles. As you can see, this increasing the loading, the value of damage increases. This is related to low number of cycle, low LCF, and this is related to HCF. And also we extracted some diagrams related to PEQ, equivalent plastic strain. As you can see, in the low number of cycle, PEQ is bigger and is more important than high number of cycles. In the end, we obtained SN curve for this material based on the strain ratio -1. This is related to experimental tests that obtained by the Padova University, and the solid line is related to the Abaqus results. As you can see, there is a good confirmation between the results. To obtain these results, we have to obtain some parameters. As I said before, there are some parameters, for example, sigma O, A, C, K, L are some parameters in high cycle, and M and Q are some parameters in low cycle. These are related to Chaboche model. Conclusion, a unified low cycle, high cycle model based on continuum mechanics is utilized. Coupling of low cycle and high cycle models due to damage evolution equation, because evolution equation is important in this case. The higher cycle part of the model is based on concept of the moving endurance surface in high cycle fatigue, and damage evolution in low cycle due to plastic information. And the model is implemented in Abaqus U-worm subroutine. This project was funded by European Union Engine Project. Thank you very much for your attention.